I am living with quadriplegia.
I broke my neck in 2006, so it's been 17 years since I've been paralyzed.
I jumped from the back of a pickup truck, unfortunately, bent my neck backwards, and here I am.
I've already lost my front teeth from years of having pens and smashing my face off of a quad stick.
When I was first injured, I was trying to learn how to use voice control to type and do all my papers and homework, and it was so frustrating. That was part of just dropping out of school.
What is out there for people with quadriplegia to use in order to interface with their computers or their smart devices? And there's almost nothing.
Tonguage is a groundbreaking, non-invasive, human-machine interface that allows for people with mobility impairments to interact with their digital devices just using their tongue. Powered by computer vision and artificial intelligence, Tonguage translates tongue movements into precise digital commands, enabling people with physical impairments to connect more freely with the digital and physical world. Imagine using your tongue to type words, interact with a computer, play games, or even operate a wheelchair. That's the power of Tonguage. Before Tonguage, various human-machine interfaces have been developed, like brain-computer interfaces, electromyography switches, eye tracking systems, and voice recognition systems. All of these systems are great. However, each of these technologies has limitations in practical applications. Brainwave and EMG signals are often inconsistent, making precise control difficult. Eye tracking, it doesn't work well in tasks that require visual focus, like gaming or driving. And voice control is unreliable in noisy environments and unusable for those with speech impairments. The human tongue is selected as our human-machine interface medium because the human tongue is controlled by the cranial nerves, which often remain functional even in individuals with high-level spinal cord injuries. Additionally, the tongue can move rapidly and accurately with less fatigue, making it the ideal medium for continuous use. To be a new human-machine interface, we define Tonguage across multiple dimensions. First is the position definition. The tongue's ability to reach different areas within the mouth allows for distinct positional inputs, enabling an intuitive and structured input system. We define 8 positions in Tonguage, which can be categorized into primary and secondary positions. The primary can be used for operations, and the secondary can be used to supplement. Second is the gesture definition. Specific gestures or postures can serve as distinct input signals, expanding the system's interaction capabilities. Gestures are categorized into 2 main types, global gestures and position-specific gestures. Global gestures are broad, system-wide actions, while position-specific gestures are confined to certain positions and are associated with more localized commands. The third is the movement definition. The tongue's rapid control movements in different ways can be used to navigate digital interfaces with efficiency. Unlike gestures, movements are more fluid and customizable, allowing for complex interactions that enhance the system's adaptability to user needs, like moving a slider or scrolling to change the volume. Fourth is the multimodality definition. It means that it can seamlessly integrate with other input methods like the nose gestures or the eye movements. This allows users to create a more customized control system based on their abilities and preferences, making Tonguage more powerful, flexible, and inclusive. Lastly, since Tonguage is used in many safety-related applications, we also define the error prevention mechanism for Tonguage, including interruption checks and focus checks. By using multiple layers of signal checks and validation, Tonguage filters out accidental movements, giving users a reliable, frustration-free experience. Whether you're typing, navigating, or gaming, every command is smooth and dependable. To establish the technical foundation of Tonguage, we proposed a set of computer vision and AI-driven algorithms. The first is a HSV adaptive threshold-based tongue segmentation algorithm. To accurately segment the tongue, the image was converted from RGB color space to the HSV color space. To solve the illumination challenges, an adaptive thresholding method was applied. With this pipeline, we can reliably isolate the tongue from the background, achieving accurate and consistent segmentation, the foundation of Tonguage's precision. Secondly, we proposed a new concentric mouth contour and cut line-based tongue orientation recognition algorithm. In this algorithm, we designed a new concentric contour model to solve the problem when the tongue does not fully cross the lips and used a cut line method to precisely determine the orientation of the tongue, which serves as the tongue keys in Tonguage position definition. The third new algorithm is the OEM-based tongue tip detection algorithm. In this algorithm, we proposed a new mathematical model called the orientational ellipse model, which uses a rotatable and flexible ellipse to simulate the tongue shapes in different directions, allowing for more accurate tongue tip detection, enhancing precision in tonguage tasks. Fourthly, we developed an MAR-based mouth open detection algorithm to introduce more gesture-based operations within Tonguage. Taking advantage of face landmarks detected using DLib, the mouth open and close gestures can be used to start and stop the program. Additionally, to support the multimodality definition in Tonguage, we developed an EAR-based eye blink detection algorithm, which can be used as additional operations in Tonguage, such as simulating the mouse click or hold. Based on its definitions and technical foundations, Tonguage has the potential to revolutionize various domains. Here we showcase some of its key applications. The first is Tongue Keyboard, an innovative hands-free typing system that enables users to input text using Tonguage. For this purpose, we designed a new keyboard specifically for Tonguage, which includes 9 tongue keys in 2 distinct modes, a typing mode and selecting mode. Users can perform different gestures to switch between different modes and accomplish tasks such as typing, selecting or starting, and stopping the program. To enhance usability, it also integrates a dynamic vocabulary bank, or DVB, which assists with word prediction and selection, reducing input effort. I tested the application in terms of recognition rate, accuracy, typing speed, and learnability. By leveraging intuitive tongue gestures and adaptive mapping, experiments show the tongue keyboard provides an accessible and reliable alternative for individuals with motor impairments, expanding communication possibilities beyond traditional human-machine interface technologies. In the second application, since nearly all individuals with mobility impairments need a wheelchair to help them move, we designed Tongue Wheel, a new hands-free mobility solution to showcase Tonguage's impact as a new human-machine interface for device control. The tongue wheel system consists of several integrated modules, including the vision module, computational module, controller module, safety prevention module, motor modules, and power module. All the modules are seamlessly connected and work together to ensure smooth and reliable wheelchair operation. The control panel interface of the tongue wheel is designed to be intuitive, allowing the user to easily adjust the direction of movements using simple tongue gestures. A server-client communication architecture is implemented to facilitate real-time data exchange between the controller module and computational unit. To evaluate the tongue wheel, we built the prototype using a Raspberry Pi, expansion board, mechanism wheels, and a combination of infrared and ultrasound sensors. We also designed a 2x3 meter course with 20 obstacles, requiring the system to complete 6 key missions, a straight navigation, turning, loop, and U-turns. The course contained 1 loop, 8 turns, 2 U-turns, and 20 obstacles. The error rate was assessed by recording collision occurrences and off-track events. Experimental results demonstrated high safety performance with an average collision rate below 1% and off-track average of 0.4 per trial, indicating precise control and effective obstacle avoidance. These findings confirm that Tongue Wheel provides a reliable, precise, and user-friendly mobility solution for individuals with severe motor impairments. Since the mouse is a critical human-machine interaction tool, we developed TonguePad as our third application, showcasing the potential of Tonguage as an alternative to traditional mouse controls. In TonguePad, we designed a unique pad control system that utilizes Tonguage's multimodality framework to handle mouse click tasks using eye blinking detection algorithm while incorporating the tongue tip detection algorithm to track the mouse movements for precise cursor control. To evaluate the TonguePad performance, we conducted a target selection experiment. We used the tongue to move the cursor and the eyes to simulate the mouse click to select 7 targets with different sizes and different distances relative to the center. The results showed an average target selection success rate of over 97% and an average selection time of 69.81 seconds across 7 tasks. To test accuracy in complex tasks, we conducted a path following experiment. We designed 4 paths from line to circles with increased mouse operation difficulties and used different padding areas to show how acceptable the region is, then to calculate how much of the path actually overlapped in each acceptable region. The results validate TonguePad as a reliable, efficient, and highly accurate alternative to traditional mouse devices. We also conducted a directional movement test. 8 target circles were placed at equal distances along 8 predefined orientations based on the Tonguage positions. The movement time and trajectory were recorded for each trial. Results showed an average movement time ranging from 2.23 to 6.57 seconds, revealing a directional speed distribution pattern, indicating variations in tongue movement efficiency across different orientations. As a new human-machine interface, Tonguage holds a vast potential across multiple fields, including smart technology, healthcare, robotics, and entertainment. By enabling intuitive, hands-free control, it can transform the lives of individuals with mobility impairments, offering them greater independence and accessibility in daily tasks, medical applications, and interactive experiences. Tongue-based HMI is a new field, especially in non-invasive, image-based applications, with no public data set for research. To bridge this gap, I'm developing the Tonguage response toward, providing critical data under varying conditions to advance algorithm and standardization, driving innovation in tongue-controlled interfaces. Tonguage stands out as a revolutionary, game-changing breakthrough in human-machine interaction, paving the way for a more accessible and inclusive future, especially for those with mobility impairments.